So as I told you, the Pythagoras theorem can be applied to the n dimensions also, and you can find out the square length of the vector for n dimension also. So it is nothing but an inner product. If I want, we had an example of 1, 2 and minus 3 or 1, 2, 3. So previous example was 1, 2 and plus 3. So similarly, I can have it for 1, 2 and minus 3. So here, if you just look, what will be the product of what is will be the length? You have to just multiply this 1 into 1, 2 into 2, and 3 into 3 minus 3 into minus 3. That is nothing but square of this, and square of this, sum all together taking a sum. So that in terms of vectors, I can represent is x transpose with multiplied with the x. So you get the same product. You can define the length in terms of length of a vector in terms of the vectors, that is two vectors. One is the transpose itself and the vector. So what are orthogonal vectors? So I here you have to check their whether they are orthogonal or not. So in one sense, in geometrical sense, you can call them whether they are perpendicular or not, or they form a right triangle. So for a right triangle, here the Pythagoras theorem also you can use a square plus b square equal to c square. So this c is your hypotenuse and a and b being the two sides. So here, the same theorem, Pythagoras theorem, can be applied. And how do you find in the sides of the right angle triangle? So you can see here, applying a length formula. This is best for orthogonality. So here, x square plus y square or x minus y whole square. This way I have right angle triangle. This is your x and this is your y. And this is in the, which I can call it as A, this as B, so it becomes your C. So you can consider the ABC as a right angle triangle. So coming to the, you can see here. So how do you find the orthogonalities? Here you consider this x square plus y square equals to and x minus y whole square here. If I have the orthogonal test, I have n dimensional vector. So I have this x square plus y square and this theorem. So here, if I am applying this, okay, if it is a right angle triangle, we will have x square plus y square and x minus y square. So you have, if this is applied to n vectors, x being n vectors and y being n vectors, automatically you will have this expression, right? So now just look into the expansion. If I expand this x1 minus y1 square, what I'll be getting? X1 square plus y1 square minus 2 x1 y1. So right hand side will be equals to left hand side, but the right hand side will have an extra minus 2 x1 y1 from the first square, and from the second from this I'll have minus 2 x1 y1 extra, and from this I'll be having minus 2 xn yn, and similarly x2 for x2 y2 and x3 y3 and so on. So these are the extra terms. If for a right angle triangle, if this has to be satisfied, that is x square plus y square, x square plus y square equals to x square plus y square, or you can say just if LHS should be equals to RHS, this LHS equals to RHS, then you have this extra term should become 0. So that extra term becomes your other condition. So you have this one. So you have RHS will be equals to this, right? X1 square, Y1 square, and we'll be having the RHS term. If LHS is having these two terms, so you have to make this term equals to 0. That becomes what? X square plus x square plus y square. So here, for each of the vector differences, I will be getting this. And this becomes your condition to check the whether the two vectors are orthogonal or not. So you can have x1 if this has to be 0, so 2 goes to, if this equation if I equate it to 0, So automatically these two get cancelled. You will have only x1, y1 till xn, yn equals to 0. So I can call this as vector x and a vector y. Either I can have a x1, y1, x2, y2. So x being the transpose and y being as it is. If I multiply them, then I will be getting it. I will be getting whether if it equals to 0, then I can say x and y are orthogonal. So that is the definition of the condition. So here uh, that condition itself has been written here, x transpose y, that is itself gives you this expression, and or it can be the summation of x1 y1, this we call it as a dot product, or this as a x transpose y or y transpose x, that means the row vector x transpose times the column vector y. If this tends to be 0, then the two vectors x and y are orthogonal. So this is the condition. We got it from the right angle triangle. So we derived this condition using what? You know the Pythagoras theorem, x square plus y square from this. And also you know that the sides of a right triangle is this, right? So using this we derive the equation or the condition for checking the orthogonality of a vector. So So you can make a note that is that x transpose y is 0 if and only if x, y are orthogonal, that as I told you. And if their value is greater than 0, then we call that their angle is less than 90 degrees. And if x transpose y, if it is giving you minus values, less than 0 values, then their angle is greater than 90 degrees. So these are the three conditions. If they are 0, it is equal to 90 degrees, and if it is greater than 0, it is less than 90 degrees, and less than 0, it is greater than 90 degrees. So the only vector orthogonal to itself is the 0 vector. So if the vector has to be orthogonal to itself, that means x transpose x is equal to 0. So every vector will be orthogonal to itself. So coming to the example, let us take an example. So here the simple example 2 minus 1 has been taken and is orthogonal to minus 1 2 2. So you have to check the orthogonal. If I check the orthogonality, that is I have kept x transpose, that is usually we write vectors in this manner 2 minus 1. When I take a transpose, it has to be written like this. And this is another y vector minus 1 2 2. This is as it is y we are writing it. And if I multiply, see here we are getting it as 0, so they are orthogonal. So the sentence satisfies the orthogonality. And you can just check the length of each of the vector. The length of each of the vector is equal to 3. The length remains same. Okay. So